Okay, we're starting with nuclear chemistry. There's lots of different ways that nuclear chemistry is used in our lives. We use it for reactors, we use it radiating food, we use it for radiation in medicine, and we use it for power. So let's learn a little bit more about it. Radioactivity, this is Marie Curie, Madame Curie. She discovered radiation. Nuclear reactions involve the nucleus, unlike regular chemical reactions. The nucleus opens up and protons and neutrons are rearranged. The opening of the nucleus releases a tremendous amount of energy that holds the nucleus together. This is called binding energy. Normal chemical reactions just involve electrons, which are on the outside of the atom, not the protons and neutrons, which nuclear reactions have. So we end up with what's called a mass defect. That is some of the mass that is converted into energy, shown by a very famous equation, E equals mc squared. Energy equals mass times speed of light squared. Okay, and speed of light is 3.0 times 10 to the 8 meters per second. One of the most important things that we need to remember is the nuclear symbol. In a symbol, we're going to have the mass number on top, and that's the protons plus the neutrons, and the atomic number on with a symbol. For example, chlorine 37 would be written 3717Cl. As part of your optional movies, there's a radiation movie. I really suggest that you watch that. Types of radiation. You've got alpha, and we write it 4,2 helium, and it's a positively charged helium isotope. We usually ignore the charge because it involves electrons and not protons and neutrons, which in a nuclear reaction we're worried about. Beta is our fancy little symbol here, beta. It is a 0, -1, mostly called an electron. It really is an electron, but it's a particle that changes like an electron would have an effect, a negative charge would have an effect. Gamma is a pure energy ray. It's called a ray rather than a particle because it doesn't affect the nucleus. A neutron is just that. It's just a neutron. It doesn't affect the bottom number, which is the protons. A positron is basically like a positive electron. I can say that really. But it's not really electron. Okay, proton is usually referred to as hydrogen 1 or 11H. Any other elemental isotope can be part of any type of radiation. So, again, really quickly refreshing on the most important ones here. Neutron is also one that's really needed. You'll notice the difference in the mass over here. These basically don't have a mass, right? Now their penetrating ability. If you look at the penetrating ability of alpha, beta, and gamma, those are our main sources of radiation. Alpha can be stopped by paper because it's bigger than the other two. Beta, you need about a 0.5 centimeters of lead. That's what they put on you as an apron when you go get your, the dentist takes pictures or you go to get an x-ray. 10 centimeters of lead is what it takes for gamma. You could also use 5 feet of concrete, and that's 5 feet of concrete is what they usually use to enclose nuclear reactors. So if I did shoot them through an electric field where I have positive and negative, beta particles, which are negative, are attracted to the positive side, and alpha particles, which are positive, are attracted to the negative side. So we can have decay. Now here's the key word, decay. Okay? If it's decay, it's going to be on the product side of the reactant. So I start with something and it falls apart. Down here on the left, we've got uranium-238, and it decays by alpha particle to get thorium-234. And we've got copper, or carbon, which decays through a beta particle to give us nitrogen-14. Now, balancing numbers are nuclear reactions is fairly easy. In the reactants, the starting material is on the left, and the products are on the right. The mass number, the top number, added together on the left side must equal the top number added together on the right side. And the bottom number, the atomic number on the left side added together, needs to add up to the atomic number on the right side added together. We fill in with missing isotopes. Let's try one. So an alpha emission. We start with radium 230 or 226. Notice this is the mass number, and this is the atomic number. I'm looking here for my mass number, and I have to add and make sure they add up to equal the same thing. Well, we've got 226, and this does add up to 226 on this side. Then I worry about my bottom number, and sorry I've switched colors, but that's okay. 88, 2, and 86. Well, 86 and 2 is 88, so it is equal, and we've got our reaction. Okay, a beta emission, same kind of thing. The top number, this arrow is like an equal sign. So they've got to be the same, and they are. The bottom numbers have to be the same. Notice this time we ended up with a bigger number on this side, so we actually had to have a negative number to bring it back down. Okay, other types of reactions. We can have a positron. Same kind of thing. The way we balance it is looking at the mass number and at the atomic number. Electron capture. This one, since it's a capture, notice that it's on the right side of the reaction. So let's do a learning check. Take a few seconds, pause the video, and see if you can do this one. Remember that the top numbers have to add up on the left to equal the top numbers on the right. The bottom numbers on the left have to add up to equal the bottom numbers on the right. Okay, let's see how you did. Did you get 13.7 nitrogen? If you did, great job. They have to have 14 on the top both sides, so we needed 13 more, and it has to be 7 on the bottom, and we had none to start with, so we needed the 7. And the 7 tells us what it is. Now here's another one. Go ahead and pause the video, see if you can do this one by yourself, and then check it. Okay, coming back. This is what you should have written. If I have an emitter, then that means it's going to give off. So this is a beta emitter, and it gives off, and I don't know why that keeps going away. It gives off a beta and something else. So we had to figure out what that was. Cobalt 60, that gives you the mass number. You just look on the periodic table to find the 27. So hopefully this is making sense. Artificial reactions, these are ones that we make happen. New elements or new isotopes of known elements are produced by bombarding an atom with subatomic particles such as a proton or a neutron, or even as much heavier particles such as helium-4 or boron-11. Reactions using neutrons are called gamma reactions because gamma rays are usually given off, and that's important to know. So if I am bombarding with neutrons, I'm probably going to get alpha radiation. Radioisotopes are used in medicine and often are made from gamma reactions, so they're also often bombarded by neutrons to get what we need. Artificial reactions, an example of a gamma reaction is written here below. Phosphorus 31 is used in studies in the body for different parts of the body. So, transuranium elements. Elements beyond 92, transuranium, are made by starting with gamma reactions. So here's a first gamma reaction. We take uranium-238, bombard it with a neutron, and we get uranium-239. Then we take uranium-239, and it gives off a beta particle because it's unstable. Then neptunium-239 is unstable, so it decays by beta and gives off plutonium-239. So this is a reaction that is used when we work with our nuclear power plants, so we get plutonium. Now, the first one we start with is known as our initiator, or thing that we start with. All these others that we made are known as daughters. Okay, they're daughter isotopes. So nuclear fission. Fission is when I bombard or hit or cause to happen something that is, I make something that is unstable, like this uranium-236 here. And because it's unstable, it splits apart into two smaller isotopes and some radiation. Nuclear fission is splitting. They're very large, so they're not stable. The fission chain has 3 goals. First is initiation. So it was hit by a neutron, it becomes unstable. Because it's unstable, then it is propagation. When it splits apart, it released more neutrons that now go and hit other molecules, making them unstable. And then we have chain reaction. So this was what happened in the 3 disasters that we've had at 3 Mile Island, at Chernobyl, and Fukushima. And those are also extra videos that you can watch. They're just short. If you don't know about them, it would be a good idea to watch those little short videos. The band of stability and radioactivity decay, the black ones in here are stable, the red ones are unstable. And you can see by where they're sort of sitting, what's going to happen to get them to stability. So in one range, I do a positron emission or electron capture to get stable. In another range, I do a beta emission. And in the higher ones, I usually do an alpha emission. So just another look at it. So as we're looking at it, this is what happens. If I'm doing a beta decay, it actually goes down 1 and over 1 to the right. If I do an alpha decay, it goes down 2 and over 2 to the left. If I do a positron decay, it goes up 1 and over 1, or an electron capture, so you can sort of see what's going on. And up to about 20, a 1-to-1 ratio is where it is stable. If I get above that ratio, then above that point, 1 to 2.5, 1 to 1.25, 1 to 1.25 is the neutron to proton ratio that's stable, and as we get higher, it becomes a little bit heavier. So the more neutrons are needed as the element gets bigger to be stable. Nuclear fission, again, heavy nuclei splitting apart, and we usually have an unstable intermediate. This is the chain reaction that we were talking about earlier. We have an unstable, we have a neutron hit a uranium becomes unstable, breaks apart, gives off neutrons, those neutrons hit more, and it just keeps going and going and going unless we absorb some of those neutrons. So nuclear fission and power. Currently there are about 103 power plants in the US and about 435 worldwide. It's about 17% of the energy comes from a nuclear power plant. And you can sort of see with that chart where they have the most, which France does have the most energy coming from it. This is an older plant model, but it gives you basically what you need to know. In the main idea for a power plant, you have to have something that generates steam. And that steam turns a turbine, the turbine puts out electricity, and then you cool down the steam and reuse it. So the purple and the blue systems, which are, the purple is secondary and the blue system is a tertiary system, these are in all power plants. Okay? The only difference is the yellow system. And the yellow system in the nuclear power plant has fuel rods and control rods. The control rods absorb some of those neutrons so they keep the reaction under control so it doesn't keep going on, propagating more and more. What is in this system in the yellow varies from power plant to power plant, but it is a closed system. So in order for radiation to get outside, the yellow system would have to break down, and the purple system would then have to break down and to get it into the environment. Now you'll see that it is in a containment shell. This containment shell is the 5 feet of concrete that stops gamma rays. So if something happens in the containment shell, we can usually keep it in the containment shell. But the problem is if the containment shell is injured or damaged in any way, like it was in Fukushima with the earthquake and tsunami. So this is where the power plants are in the US, and that sort of gives you an idea. Here in Utah, we really don't have any around us anywhere close, but back east there's a lot more, and there's a lot more demand for energy. I did put these videos up on the website, so it would be a good idea to look at those. Nuclear fission, or fusion, now is taking 2 things and making one, so it's basically opposite of fission. So I'm going to take 2 and smash them together and get something new, and it also gives off energy, and usually a gamma ray. So I could take 2 helium, smash them together, and get a beryllium. Take a helium and beryllium, smash together to get carbon. This is sort of like the Big Bang theory, where The most abundant element in the universe is hydrogen. The second most abundant is helium. The third most abundant is lithium. And for the most part, it follows down that way. The reason why is I have to take two hydrogens and smash them together to get a helium. And then I have got to take a hydrogen and a helium and smash them together to get a lithium. And then I take two hydrogens or two heliums, smash them together and get beryllium. So to get all the elements on the periodic table, all these elements have got to smash into each other and make bigger elements. Fusion power, there's a video on that too, and you can check those out. Most of those videos are like 5 minutes, most of them. There's a couple that are a little bit longer, but you just need the main idea on those. So fusion, excessive heat can't be contained. That's the problem. It's the sun. It's a continual amount of energy given off. So attempts at cold fusion like we had at the U of U have failed. They have said in the last couple of years that they've figured out how to do that. I'm still waiting to see. Hot fusion is difficult to contain. I just like this Red Rover cartoon, Twinkle, Twinkle, Little Star, How I Wonder What You Are. He looks up in the encyclopedia, a gaseous sphere of mostly hydrogen, helium with carbon, nitrogen, and oxygen, and iron thrown in. So just remember, the most abundant element in the universe is hydrogen, second most helium. A half-life is basically, if I have an unstable atom, how long does it take for half of that mass of unstable atoms to decay? Pretty easy. So the rate of reaction of a nuclear transformation depends on the reaction concentration. Half-lives are different. Some half-lives are really short, like 3.8 days. Some are extremely long, like 1.25 times 10 to the 9 years. So depending on the element depends on how long it takes to decay. So here I have a exponential decay chart, which is what decay would be for a half-life decay. And you see 500 million years and 1.26. Each time I decay by half. And we're going to do a little lab or activity that will help you understand that. Another half-life thing, the decay of oxygen-15. So we have ways that we can detect radiation. We've got what here is shown as a Geiger counter. Say that I started with 50 grams of radium-234. And it has a half-life of 3.6 days. How long till I had half? Well, 3.6 days, right? So I'd have 25 grams after 3.6 days. And if I wait another 3.6 days, I'd cut that in half again, and I get 12.5. And if I wait another 3.6 days, then I cut that in half, and I get 6.25. So every time you just cut it in half. So here's a learning check. Stop the video, try it, and then come back and see if you got it right. Okay, so on this one, basically all you're going to do is you see the half-life right here is 13 hours. And you've got 39 hours. So if you take 39 and divide it by 13, you get 3. So you're going to take and cut it in half 3 times. So I take 64, divided in half is 32, divided in half is 16. So here's 1, here's 2, and the last time is 3, and I get 8 milligrams is how much I'd have left. Okay, so some effects of radiation, some things that they worry about. Now with Fukushima, that's really close in your brain. So 0 to 25, no effect. 26 to 50, you get a small decrease in the white blood cells, not a big deal. 51 to 100, you get significant white cell, blood cell count decrease and lesions. When you get to 101 to 200, you get loss of hair and nausea. Chemotherapy and radiation, that probably sounds familiar. But once you get past 200, you get hemorrhaging, ulcers, death, and in 50% of the population above 500, it's death. Okay, so radiation danger, normal natural sources. We've got rocks and soil around us. Marble is one of those ones that gives off a lot. We've got radon. We have that problem here in the Mountain West. Cosmic rays, we don't have any control over. Radioisotopes in the body. We actually eat a lot of salt that has iodine and stuff that's radioactive and other things. Now, human-made, we put ourselves into this by having x-rays, by having nuclear medicine, and actually eating some of our food that is prepared. So Geiger counters were used to detect Even things that some plates and stuff from Mexico actually had radioactive plate in it a few years ago. So here's another list of things. Even looking at TV tubes and watch dials, you get stuff. Okay, so radiocarbon dating. Say I wanted to find out how old something was. Radioactive carbon dating, carbon-14, is formed in the upper atmosphere by nuclear reactions initiated by neutrons, and we get carbon-14 from nitrogen-14. It is oxidizing CO2, which circulates through the biosphere. When a plant dies, the C14 is not replenished, so we can find out how something old is by how much C14 is still left in it. The half-life is 5,730 years. So activity of a sample can be used to date a sample. We also use thyroid to find the thyroid, how the thyroid's working. We use technetium-99. We use cobalt-60 to disinfect meats and foods. We radiate food with cobalt-60 and cesium-137 to kill bugs, so that has a longer shelf life. Like irradiated milk has a shelf life of 3 months without radiation. And the USDA has approved radiation of meat and eggs, so it'll last longer and travel across the country. We make artificial elements by bombarding it with things. And this looks good, man. I'm going to make me some gold. Well, it takes a lot of energy to make that gold, and it's a lot more in cost than that gold is worth. Okay, they are produced in particle accelerators, so you have to have a real lot of energy. Here's one accelerator in Chicago, Illinois. There's one in Batavia, Illinois. A linear accelerator in California, Stanford. And there's one that goes underneath France, in Europe, 3 or 4 countries, and they all have to agree because it takes so much power to run it. So that's the end of this, and we'll see you in class.